So here's what we're just going to kind of work through these four scenarios. Let's just start with the big idea. For a spontaneous reaction, what's the sign of delta S for the universe? Positive. Okay.
No, I
So
said
good.
positive.
So good at this.
Now, what about delta G? You say that with no confidence whatsoever.
Yeah.
It has been a minute, hasn't it?
Where's the
G at?
It's in the notes somewhere.
All right.
With the sign.
Now,
Negative.
so here's what we're going to work through are these four different scenarios, okay? So, we're going to
I
start
like the low and the high.
It's right here.
It's a nice touch.
with, I know, we got that.
It's right here.
So, we're going to start with the one that is always spontaneous, okay? So, this is a kind of a math problem more than anything. So, I'm just going to make up a number, and I'm going to say delta H is going to be a value of negative 5, okay? Don't worry about the unit, it's just negative 5. So, if you know delta H is the value of negative 5, endothermic or exothermic? It's
Exo.
exothermic, right? So this is going to be an exothermic reaction. Okay? Cool. Now, in this situation, I'm going to let delta S be 8. Okay? Just to pick up a number. So delta S is positive. These are related, but these are two different ideas. So you can't look and go, oh, I have a negative delta H, and then that's going to influence the delta S. We have them combined in the same reaction, in the same equation, but one does not influence the other. Here's the main thing I want you to get. If you have a positive delta S, are you increasing or decreasing entropy? Increasing. So we are going to increase disorder. Okay? Now, for the sake of simplicity, let's say the temperature is 10 degrees Kelvin, okay? Which is really, 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 really cold, but it's going to make the math work out, okay? So, here's what I've got. So I'm going to calculate delta G for this. So delta G is going to equal my delta H, which is going to be negative 5, and typically that's kilojoules per mole, minus my temperature, which is 10 degrees Kelvin, and then my entropy is going to be 8 kilojoules per mole Kelvin. So everything's going to be in kilojoules per mole. So the kelvins are going to cancel out. So I'm going to have negative 5 minus 80. So what am I going to get? Negative 85, right? Kilojoules per mole. Is this reaction going to be spontaneous?
Yeah.
So in this situation, if I raise the temperature up to 100 degrees Kelvin, am I still going to get a negative delta G? Is there, even if I drop the temperature to 0, if I drop the temperature to absolute 0 Kelvin, am I still going to have a negative delta G?
Yeah.
Okay, so this is a situation that Mother Nature likes a hot mess. Okay? Mother Nature is a hot mess. So what's happening is that you have an exothermic reaction, so you have a negative delta H. Mother Nature goes, that's nice, exothermic, this is cool. Okay, Grandma, Mother Nature's old, okay, she gets cold easily. She's not cold, baby, go give me my sweater, okay? So Mother Nature wants to be warm, okay? Mother Nature has also reached the point in her life where she just doesn't care about a mess, okay? She's not going to worry about it. It's like, I'm cold, baby, and I don't want to clean. So Mother Nature wants to be warm and have a mess. She likes fireworks, okay? Ooh, ah, exothermic. Ooh, big flash, right? So Mother Nature is a hot mess. So this combination of a negative delta H and a positive delta S is always spontaneous. So, and I don't care how, I'm going to give you a couple of options of how you understand this. One is mathematically. So here's the nerd language for how you explain this. So when you have a negative delta H, here's the nerd language. You say the reaction is driven to spontaneity by the enthalpy term. Okay? So when you have a negative delta H, Mother Nature is going, cool. We're going to get warm. It's nice. Okay? So you have a negative delta H. That means the delta H term is driving it towards spontaneity. If you have a positive delta S, it's the exact same statement, but then you say the reaction is being driven towards spontaneity by entropy. Okay? So a negative delta S, or excuse me, negative delta H, Mother Nature's digging it. Exothermic reaction. Positive delta S, you're making a mess. It's cool. Okay? Mother Nature's a hot mess. This is the perfect combination. So if you have these two terms, the reaction is always going to happen. Now, that doesn't mean that it's spontaneously going to happen. Like, for example, hydrogen and oxygen. If we just randomly mix hydrogen and oxygen, it isn't like we get an explosion, okay? That would be bad. It's like, oh, no, we can't react zinc and hydrochloric acid because the hydrogen bubbles are going to spontaneously react with oxygen in the air and make explosions, okay? That doesn't mean you don't have activation energy. That doesn't mean that you don't have to start the reaction. But once you start it, it's going to proceed towards that end. Okay, so there's going to be 4 combinations. If you're into flashcards, this might be one of your flashcards. This reaction is always spontaneous. You have negative delta H, positive delta S. Mother Nature goes, winner, winner, chicken dinner. Now, the other option is if you have a positive delta H and a negative delta S. Okay, so now we're going to look at this. So now I'm going to make the delta H be a positive 5 kilojoules per mole. I'm going to make my delta S be a negative 8 kilojoules per mole, and we'll still let that temperature be 10 Kelvin. So now when I go to calculate delta G, I'm going to have 5 kilojoules minus 10 times negative 8 kilojoules per mole Kelvin. So I got 5 minus my Kelvin times the negative delta S. Mathematically, what is always going to be the sign of delta G for this combination?
Positive.
Positive. Now, in this situation, it's just the opposite of what we just talked about. Your enthalpy term, because it's positive, is that an endothermic or exothermic reaction? Positive delta H.
Endo.
It's endothermic, okay? That's driving it away from spontaneity. Because Mother Nature is going, oh, baby, I'm going to get cold, okay? It's endothermic, right? So Mother Nature's not digging it. I got to get my sweater. It's cold. So not only is Mother Nature going to be cold, we're making Mother Nature clean. She's pissed at this point. Okay? She's going to have no part of this. Like, I'm going to be cold and you expect me to clean. Mother Nature will have no part of this story. Okay? Not going to happen. So both the enthalpy and the entropy are driving Mother Nature away from this combination. Mother Nature has no positive things about nothing. Nothing is working in her favor. It's not going to happen. So let me give you an example. Those of you that have been through AV Bio, what are some big elements that make up like a tree? What would you need? If I said, hey, we're gonna make a tree, what elements might you need? Maybe some carbon? Yeah, the entire tree. So you gotta have so we need some carbon, maybe some nitrogen, maybe some oxygen. Let's start with those three, okay? You need some hydrogen for the hydrogen bonds, okay? So,
You know, that's a tree, definitely.
so here's what we're gonna do. We're gonna take like a 5-gallon jug, okay? And we're gonna introduce some hydrogen, some charcoal to get the carbon, a little bit of nitrogen from the atmosphere, and some oxygen, okay?
Oh, I thought it's a tree.
And here's what we're gonna do. So we've got the main constituents: hydrogen, carbon, nitrogen, and oxygen. And we're gonna shake it around, okay? What are the odds of all of a sudden, oh look, there's a tree inside?
Zero.
Zero,
Not zero.
okay?
You never know.
I mean,
Very low, but it's never
we're in a class of magic, so
true.
whatever happens.
There's literally fairies.
Okay, but odds are, when we do this, it isn't like, oh look, there's a tree. Okay?
How big of a tree are we talking? It could be a molecular tree.
How do we shake?
A tree that you can see.
How do we
Once
define
I
it?
turned 18.
I think you know what I mean by tree.
What?
So that combination is not going to happen, okay? Now, but I take a tree and I put it in there, a small chunk of the tree, and I throw a match in there. That's just a bit of the tree. And I throw a bit of the tree in there with a match, what's gonna happen?
I mean, charcoal will catch fire,
Oh,
but
now that's gonna burn, right? So what's gonna happen? What's gonna
Char.
happen?
Oh my gosh, you get
Charred
carbon
tree.
as hydrogen.
Oh! Is that gonna be an exothermic reaction?
Yes.
Yes. Yeah, if you're out in the woods and you have some trees and you want to burn them,
She does casually.
Just
That happens
casually.
a lot to me.
okay, it's gonna release energy, right? That's an exothermic reaction. It doesn't take energy in. It's like, man, I'm hot. Let's go light a fire. That'll cool down the house. No, okay?
You never heard of Smokey the Bear?
No.
Smokey the Bear told us not to burn forests.
Only you.
Okay,
Not a big.
so,
No?
Who's Smokey the Bear?
You don't know Smokey
They don't know
the Bear?
Smokey the Bear?
Come on. Do you know
who
Smokey
doesn't
the
know
Bear?
Smokey Bear?
Who is Smokey the Bear?
Yeah, see?
I don't know.
How do you go through your life
Look up
without
Smokey
knowing?
the Bear.
Please, Bert. Yes, let's go, Bert. How do you not know
Smokey the Bear either?
What do you not know Smokey the Bear is?
What is this generation coming to? This is why we have forest fires in California.
Amen.
Maybe I have.
The kids from Maze, Kansas are the reason.
Yeah, kids from Maze, Kansas.
California.
Smokey the Bear.
Never seen that.
I love
Only you can prevent
Created in
forest fires.
1944,
The zoo used to give
and the
out
motto
Smokey the
was,
Bear
only
cups.
you can prevent forest
Where?
fires.
remember learning about Smokey the
By
Bear.
the gorillas.
I never knew.
Yeah, I was-
Anyway, so there's your cultural lesson for the day, Smokey the Bear.
I still don't know who that is. What's the point? It's just a bear that says only you.
Only you can prevent forest fires.
Bears live in the forest.
So you don't
burn down
no
He actually helped a
wildfires.
lot.
I love that.
Actually,
Raised awareness.
so, and the argument is it actually went too well, because then
You know, because
didn't
fires.
use Okay, anyway,
What would you need?
Firefighter bear.
Firefighter bear?
I know who they can dress up as Smokey.
See, that's a better
My
way
favorite
to Smokey the bear.
No one wants to listen
Morgan's from the Firefighter.
The bear.
I like that.
That's not
If
practical.
somebody,
That's a very kind of forest fire.
if somebody,
That's why he's telling us. That's why he's telling us that we
yeah,
have
because
to
the bear
protect
lives in the
forest.
forest, so he wants us to protect it.
So you name him Bear Guy. That doesn't make any sense.
I,
That means that he's probably the one smoking. He's making the fire because he's smoking.
So the bear's smoking.
He's going to if you don't prevent forest fires. He's gonna be dead. He's gonna be burnt to charcoal.
You see, that his entropy would increase because he's no longer a solid.
Anyway, just let it go.
Breaking news, Smokey the Bear died of lung cancer.
Back to our story. Okay. Back to our story. Now, if I raise the temperature to 100, is it still going to be non-spontaneous?
Yeah.
So is there a temperature that I can reach where I generate a negative delta G?
No.
Absolutely not. Now, here's the other thing we're going to do. Delta G equals delta H minus T delta S. So, if delta G equals 0, what do you know about the system? It's going to be in equilibrium. So, now I'm going to transition into the next two sets of conditions. 0. So if you can reach a point of equilibrium, you have delta H minus T delta S. So I'm going to move this over, and I'm going to get T delta S equals delta H, okay? And temperature is going to equal delta H over delta S. Okay, now let's look at the units. So delta H is in kilojoules, right? Delta S is in what? Kilojoule, that's per mole. That's kilojoules per mole Kelvin. Whoa, Kelvin flips up, we get temperature.
Fractions.
Whoa, yay for fractions. Now, because we're in Kelvin, can you ever have a negative Kelvin?
No.
No. So, here's what I want you to see. If you look at that first combination that we did, we had a negative delta H and a positive delta S, right? So with that combination, I can never find a temperature that will work because I'm always going to generate a negative temperature. If you look at what we just did, where you had a positive delta H and a negative delta S, that also will not produce a positive temperature. So the only way that I can get a temperature that's positive is one of two things. Either I have a positive delta H and a positive delta S, or I can have a negative delta H or negative delta S. So when you have these combinations, okay, when you have these combinations, that means it's temperature critical because I can find a temperature that satisfies this condition. So this is why when you have the negative delta H and the positive delta S, that's always spontaneous because it isn't temperature critical. If you have a positive delta H and a negative delta S, that's never going to happen, so it isn't temperature critical either. So what we're going to look at now are the ones that are temperature critical. So, go back to this. Delta G equals delta H minus T delta S. Now, we're going to have delta H. What were the numbers I had? 5 and 8. Okay? Delta H is going to equal 5 kilojoules per mole. Delta S is going to equal positive 8 kilojoules per. Actually, I'm going to make that 15. Just going to make that'll work it out a little bit easier. Okay, so here's the story. So I got a positive delta H and a positive delta S. Which of those terms, enthalpy or entropy, is driving it towards spontaneity?
Enthalpy. Entropy.
Entropy, why?
Because it's an endothermic.
Okay, it's an endothermic reaction, which Mother Nature does not like. True?
And the entropy
True.
But Mother Nature is gonna be cold, but we're gonna make a mess. Okay? So in this reaction, here's how you would say it. It is being driven towards spontaneity by entropy, because that's a positive value. But it's being driven away from spontaneity because you have a positive delta H. So your delta H is going, Mother Nature is going, not digging this, okay? But the entropy is, she's going, well, I am going to make a mess, so maybe I can make this work. So here's what I'm going to do. I'm going to let, for the sake of argument, I'm going to let the temperature be 2 Kelvin. Okay? The math is going to work out. So I'm going to have delta G equaling 15 kilojoules per mole minus 2 times 8 kilojoules per mole. Okay? So if I do this, what am I going to get for my delta G value?
Negative.
15 minus 16, I'm going to get -1. Is this reaction going to be spontaneous?
Yes.
Yes. Okay? Because I'm going to get a negative G value. Okay? Now, what if I let the temperature go to 3 degrees Kelvin? Am I still going to get a negative delta G?
Yes.
Right? So no matter what I do with that temperature, 3, 4, 5, I'm going to get negative delta G, which is going to be spontaneous. But, what if I lower the temperature to 1 Kelvin? Okay? So now I want to drop the temperature to 1. So now I'm going to have delta G is going to equal 15 minus 1 times 8 kilojoules per mole. Got 15 minus 8. What am I going to get?
7.
Positive or negative?
Positive.
Positive. So now I've got a positive delta G. What's going to happen? Will the reaction happen? No. So if I drop the temperature too low, the reaction isn't spontaneous. But if I'm above a certain temperature, the reaction is spontaneous. So do you think I could find a temperature where delta G equals 0?
Yeah.
Yeah. Set this side equal to 0. Okay, cool. So if it's going to be temperature critical, we're going to go through a phase change. I'm going to have 0 equaling 15 minus T times 8. Add that over, I get 8T equals 15. T is going to equal 15 divided by 8, otherwise known as, what's 15 divided by 8? Take 15 and divide it by 8.
1.875.
1.875. So at 1.875 Kelvin, the system's going to be in equilibrium. This would be like 0 degrees Celsius, okay, or 273 Kelvin, on a phase change from water to ice. Boiling water. Oh, I'm going from a liquid into a gas. So when you can find a critical temperature, that means that's where you can reach a point of equilibrium where you might, and again, it depends on the situation. Don't think it's always boiling or it's melting. But it's typically, that's what's going to be associated with the phase change. So here's the point. Notice that I have, in this situation, 2 positive values. I have a positive delta H, and I have a positive delta S. So when you have that combination, that means it becomes spontaneous at higher temperatures. Okay? Now, when I say high temperatures, don't think that that's, only if it's like 5,000 Kelvin or the surface of the sun, okay? When I say higher temperatures, all that means is that it's above a certain threshold. Because what has to happen, if you're a math nerd, what has to happen is that I have to let the T delta S get big enough so that when I subtract it from delta H value, I get a negative number. Okay? So that's why I have to let that part of it get bigger. So that's why it has to become a higher and higher temperature. So this is a classic example. Oh, I want to melt ice. What does the temperature have to be above? 0. Oh, that's a spontaneous reaction. So if the temperature is like at 5 degrees Celsius, oh, melting ice becomes spontaneous. If I'm at 0, the system's at equilibrium. And if I'm at -5, is the ice going to melt? No. Okay, so stop you on the camera. I know you've been sitting. Take a stretch. We've got one more to work through.